Okay, right, let's look at a bit more integration then. And we're now going to look at a bit of integration by parts. So I'm going to just write up the by parts formula, which is if we have the integral. So where substitution and recognition were used for kind of undoing a chain rule, by parts really is for an inverse of like a product. Okay, so we have a product here, but we have to treat part of it as a function which we're going to differentiate and part of it as a function which we're going to integrate. So we set them as u and v dash. So if u is 6x, then u dash is equal to 6, v dash is equal to cos 3x. And v, by integrating that, a bit like we did earlier by recognition, would be what differentiates to cos 3x, and it would be a third sine 3x. Okay, and now I put those in accordingly. So the reason I chose u to be the one differentiated is when I get u dash, it gets simpler. So it makes this integration over here as easy as possible. So let's plug that into the formula. So u times v would be a third sine 3x times by 6x minus the integral of v du dx, or vu dash, which is a third times 6 with respect to x. So 6 times a third would just be 2 sine 3x minus, and then I'm going to take the factor of 2 out, 6 times a third, and I've got sine 3x, which I'm planning on integrating. So that would be what integrates to sine 3x minus cos 3x, but by chain rule and recognition, it would be a third of that. So minus a third cos 3x. So my final answer is 2 sine 3x minus 2 times minus a third. And then this bit will tidy up. And that's it. So where does the by parts formula come from? We're going to have a little look at now. If I take, for example, a product, if I have a product u times v, and I differentiate this with respect to x, we should all know by the product rule that I would get u dash v plus v dash u. Now, if I integrate both sides there, I integrate the derivative, I just get the thing. If I take integrals of all of this. So that just leaves me with uv is equal to the integral of u dash v plus the integral of v dash u, all with respect to x. Now, if I basically just make one of these the subject, so if I say make this the subject and I move the other bit to the other side, then I get the integral of v dash u is equal to uv minus the integral of u dash v. So basically what I'm saying is this integration here, some product of a derivative and an integral, or two functions where one's been differentiated, is equal to all of this. And this is kind of what I'm applying when I do by parts. I'm saying the integral of uv dash, or v dash u, is the product of the two things before either of them have been differentiated, minus this integral of the other way around. And I use that understanding of a reverse to help me integrate things that involve products, setting one as the derivative and one as the function that hasn't been differentiated yet. Okay, so here we're going to need to use by parts twice. Again, this is the one I'm going to set as u, and this is the one I'm going to set as v dash. Now, the reason I set u as equal to x squared and v dash as equal to e to the x, again, in most cases, I will set the thing to do with x as the one I differentiate because it gets simpler, whereas e to the x differentiated or integrated gets no simpler or any more complicated, it just stays the same. So that's quite easy because that means v is equal to e to the x and u dash is equal to 2x. Okay, so what I get here is the integral of this becomes u times v, so x squared e to the x, minus the integral of the other way around, v du dx, so 2x e to the x with respect to x. Now the problem here is this can't be integrated straight off. This is another by parts. So this is by parts twice. We've got to do another round of by parts. So for this bit now, I'm going to do the same thing again. This time this bit is u, this bit is v dash. And I do this bit plugged in. So I do uv, which is 2x e to the x, minus the integral of v du dx, so 2e to the x with respect to x. And remember, I was minusing all of this away from x squared e to the x. So now let's finally solve that. So solving that, we're going to get x squared. That's a minus times a minus, it's a plus. And there we go. So that's using by parts twice. So we need to be careful there because it kind of took 2 rounds of by parts for this bit to kind of go to something that didn't involve x anymore, that we could just integrate straight off. Right, loopy by parts, here we go. These are really cool, these types. So it's a bit of a weird one because there's no obvious way to set this up. So we could do it either way. Let's say u is equal to e to the x, u dash is equal to e to the x. Then v dash is equal to sine x, and v is equal to sine x integrated, which is minus cos x. Now, if I plug this into by parts, u times v is minus e to the x cos x, and I'm minusing the integral of v du dx. So that would be minus cos x times e to the x. And now what you might think is a bit strange about this one is this bit here looks no simpler than the first one. And that is a problem with this question because cos and sine kind of fluctuate between each other when you differentiate, and e to the x doesn't get any simpler. So we're going to have to employ a kind of new trick for this one. Right, so again, we're going to do our second round of by parts. So for this bit, I'm going to do the same sort of thing. I'm going to call that bit u and that bit v dash. And what I might do is I might actually take that out and put it as a plus, take out the factor of minus. Minus times a minus is a plus. And so integrating this bit, I get uv minus the integral of v du dx And then we kind of get to the stage where we think, hang on, this is going to go on forever. Okay, so if I put this all together, this is where a really cool trick comes into it. Okay, at this stage, I was trying to work out this integral. So let's rewrite the whole thing that I have going on here. I've got that the integral of e to the x sine x is equal to minus e to the x cos x plus e to the x sine x minus the integral of e to the x sine x with respect to x. So if I add this thing that I'm trying to integrate to this side, what I end up with is basically 2 lots of that same integral. So 2 lots of that integral equals all of this. So 1 lot of that integral is all of this divided by 2. Or in other words, and then plus c. Cool, right. So now we're going to just look at a partial fractions question. And to start with, let's remind ourselves how we actually write this in partial fractions. It is kind of guiding us what to do. So let's have a little look. That needs another x plus 1 and an x plus 3. Okay, so let's compare what's going on the top. Right, and by subbing in values cleverly, let's sub in x equals minus 3. So c is equal to minus 3. So c is equal to minus 3. Let's let x equal minus 1. So a equals 2. Now, if I know a and I know c, I could sub any other value in, or I could kind of equate coefficients, whatever works best. So b equals 1. Okay, right, so let's write this up then. And now let's integrate it. So I was asked to integrate this, but I now know that's the same as integrating all of this, which surprisingly is much easier. So here we go. I'm integrating okay, so this one is going to be the kind of recognition chain rule backwards. If I differentiate that, to get my adjustment factor, I would get minus 1 lot of x plus 1, so I need to times it by minus 2. This one is going to be the natural log of x plus 1. We should hopefully recognise that. And then this one is going to be minus 3 lots, the natural log of x plus 1, and then plus c. So this is it integrated. We can tidy this up using log rules. Okay, and there we go. Right, I hope that was useful. Integration is a massive topic, it is tricky, but keep working at it. There's so many resources you can use to practice this, so make sure you do, and it brings everything together, so it reinforces your differentiation as well. Okay, great, so well done with that. Keep working away at it, and hopefully there'll be some more videos soon. Integration is a massive topic, and as I've said before, all the topics kind of come together at the end, so it all kind of builds into this topic. Remember, when you're doing calculus with trig, you need to be using radians. Make sure you keep that in mind for any of these questions. And well done again.